All right, everybody, this is our video kind of introducing heat and temperature. Now, a lot of this is going to be feeling familiar from chemistry, but we're going to kind of take a more precise energy look at things and specifically considering energy conservation at the microscopic level. So let's start with temperature. That's not how you spell temperature. Temperature. There we go. Okay. So thinking back to chemistry, specifically ideal gases, we know that the temperature is related to the thermal energy of the object, right? Which at that very small level is related to the kinetic energy of the molecules. Okay. So you may have learned this equation in chemistry, depending upon what level of chemistry you're in, but we can actually calculate the kinetic energy of the molecules in a system by doing 3/2 N, where N stands for the number of moles or amount, right, times Kb, which is Boltzmann's constant, times T. Now, we're not actually going to use this equation. What we are going to use is the relationships within this equation. So what's important to know is if I was to, say, double the mass, that would lead to a doubling of that kinetic energy or a doubling of the thermal energy. Okay? Because if I double the mass, then I'm going to have twice the number of molecules. Similarly, if I triple the volume, then I'm going to have 3 times the kinetic energy or 3 times the thermal energy. Okay? Kb is a constant, so that's never going to change, right? But this temperature T is in Kelvin. We'll talk about the different scales in a second, right? So if I double the temperature, then that's going to mean we got twice the kinetic energy or twice the thermal energy. Okay. So again, we're not going to necessarily calculate with that equation, but it's important to know the kind of relationships that exist within that equation. So I mentioned Kelvin, and Kelvin is one of our temperature scales. So Kelvin is based on the fact that 0 degrees, also known as absolute zero, is the point where all molecules stop moving. Now, we have gotten very close to 0 degrees Kelvin, but we have not gotten to a point where we can freeze all of the molecules. So that means the molecules stop vibrating back and forth, the electrons stop rotating around the nucleus, so on and so forth. So 0 degrees Kelvin, super, super cold. That's based on absolute zero. So then we have the Celsius scale, right? And that's based on 0 degrees as the freezing point of water, and 100 degrees is the boiling point of water. Okay. To go between Kelvin and Celsius, it is a linear scale, meaning they vary linearly. Specifically, if I wanted to figure out the degrees Kelvin, I would take the degrees Celsius and add 273. Not too bad. So Celsius is based off of information about water. Then we have the Fahrenheit scale. Right? And for some reason, this dude Fahrenheit was like, I disagree with the simplicity of 0 and 100. I'm going to make 32 degrees the freezing point of water. and 212 degrees, the boiling point of water. Okay. So 0 degrees is just cold, and 100 degrees is just hot. It's not meaningful, right? The meaningful temperatures in Fahrenheit are 32, the freezing point of water, and 212, the boiling point of water, right? Now, this number should seem very high to you. That is why steam is really, really dangerous and why you can get burns from steam, because it's really, really hot. Now, converting between Celsius and Fahrenheit is not that easy. It is not a linear scale, meaning we don't just add or subtract a number. We have to multiply by some stuff. So degrees Celsius is 5/9 Fahrenheit minus 32. Okay. Complicated. Now, in science, we use Kelvin and Celsius because they make sense, right? It's like we use the metric system because everything varies by a factor of 10, whereas the English system is just weird. So those are our temperature scales. So along the lines of temperature, what I would like you to do is rank the following objects with regard to temperature. Right, so you're going to touch them and rank them based on temperature. So let's do the chair leg, the tabletop, maybe the chair seat, and we'll throw the floor in there. So you're going to touch those different objects, and you're going to rank them regarding to temperature. So pause the video here. All right. Now, unpause. Now, you probably felt these different things, and you said, well, the chair leg feels really cold, so that must be at the low end of temperature, and the chair seat feels hot, so that must be at the high end of temperature, right? So you might have ranked them differently, but let's keep in mind, are they all in the same room, right? And they've been in the same room for a while. So aren't they all at air temperature? Right? So all of the objects you touched are actually all the same temperature. Okay? Now, the chair seat might be a little bit hotter because of you sitting in it. Some of your body heat could have transferred to the chair seat. But if you had just sat down, all of those things would be the same temperature because they've all been in the classroom for a very long period of time. Okay, so things feel colder because of a transfer of heat, not because of a temperature. Okay? So the greater the rate of heat transfer from you to the object, the colder the object is going to feel. So that's why the chair leg feels the coldest, because metal can transfer heat very quickly. Okay? So let's talk about that word heat. Heat is a transfer of thermal energy. Okay. So there is an action involved with heat. There is a transfer of thermal energy. So it's not okay to say, oh, this object has a lot of heat. That is meaningless. It is okay to say, oh, this object transferred a lot of heat to the environment. Right? There's an action involved. Okay. So let's talk about how we heat objects, methods of heat transfer. So here we have a video of some boiling water. Okay, so there is a hot plate here. We have a beaker. We have boiling water. There's something in the beaker. I'm not really sure what it is. We'll ignore that for now. Right? But we're just thinking about how did that water get to boiling, right? How did we transfer from the hot plate and so on and so forth? Okay. Now, these are words that you should know from prior science classes. Now, of course, first and foremost, in the hot plate, there is a transfer of electrical energy, right, from plugging it into thermal energy, the hot plate actually getting hot, okay? So that's kind of an energy conversion taking place. But I want to think about how is the energy going to transfer. Okay? So let's think about the hot plate to the beaker to the water. Okay? Now this might be the most common form of heat transfer that you are used to. The hot plate is touching the beaker, which is touching the water, and therefore we transfer heat via conduction. Okay, so this is thermal energy transfer via contact. Okay, so in conduction, we always move from hotter objects to colder objects, right? We heat from hot to cold. Okay? So when the object is hot, thinking back to what we talked about in the very beginning, we have those faster moving molecules. And so those faster moving molecules transfer some of their kinetic energy to the slower moving molecules. Right, transfer KE, allowing those slower moving molecules to speed up and therefore increasing the temperature of the object. Okay, so that's conduction. We need to be in contact. So let's think about in the water. So within the water itself, we have convection, right? This is thermal or heat, thermal energy transfer or heat via currents. Okay. So within that beaker of water, we have something less dense fluid rising and something more dense fluid sinking. So think for a minute about what should go in those blanks, right? So what should go in those blanks is hotter, less dense fluid rising, and conversely, colder, more dense fluid sinking. Right? And we end up with this current. Okay? So the rising hot water pushes the less dense cold water down to the bottom. Now at the bottom, the water is in contact with the beaker in contact with the hot plate. So at the bottom here, right, we have, we'll call it a conduction zone. And the various bits of water get heated because of convection, because of this current, right? This is also why the second floor of your house is probably going to be hotter than the first floor of your house. And we especially notice that in the summer, especially if we don't have AC. So that's convection. And then last but not least, we have the hot plate or the water to the air. That happens via radiation. Okay. And this is a transfer of energy. Now, what's really cool about radiation is we can transfer thermal energy, but we can also transfer different kinds of energy as well, right? It's called electromagnetic energy, right? So it's just transfer of energy through electromagnetic waves. And these are caused by vibrating particles. So in the hot plate, as the hot plate heats up, the individual particles in the hot plate start vibrating faster and faster, and those vibrating charges create electromagnetic waves, which allow for the transfer of energy through space. Now, what's really cool about radiation is we can transfer energy through actual space, right, where there is a vacuum. Okay. The other two forms of energy transfer, they require matter to be present in order to transfer the energy. Right? Radiation does not require matter to transfer the energy. The energy is transferred via waves. We're going to talk about waves more later, but waves transfer energy, not matter. Okay. So let's think about the microscopic level. Okay. So initially, we have beaker, and let's just say that's some room temp water on the hot plate. Okay. The hot plate is hot because I colored it red. So if we think about the thermal energy or the kinetic energy of these hot plate particles, right, these are going to have a lot of kinetic energy, right? Now, when we have solids, the kinetic energy is going to be related to the speed of the vibration of the particles in the solid. Because we know in solids, those particles are kind of stuck in place. So instead, they vibrate back and forth. The more kinetic energy they have, the faster they vibrate back and forth. Right? So in the beaker, we'll kind of give the beaker some shape, and in the water, those individual particles are moving slowly. Now the beaker's a solid, so it has particles that move back and forth. But the water is a liquid. And gases, Ke is going to be proportional to the linear speed, meaning the particles are going to move in straight lines faster, because in liquids and in gases, the particles can actually move around, right? So I'm only going to draw an arrow going in one direction for the water, because they don't necessarily vibrate back and forth. So after this has been going on for a while, what we would expect is these hot plate ones are still the same because it's being fed continuously with energy. And now the beaker ones kind of match the temperature of the hot plate, as do the water particles. Now these all happen because of collisions. The particles in the hot plate at the very edge of the hot plate are colliding with the particles at the very edge of the beaker. The ones at the very edge of the beaker are colliding with other ones within the beaker. And then those ones on the edges of the beaker are colliding with particles in the water, allowing for a transfer of energy. Okay. So this energy transfers because of collisions. Right? Collisions are really kind of the cause of everything. Okay. So we got thermal energy, which is related to temperature or the kinetic energy. Another energy that's going to come up that you're going to read about is internal energy. Now, sometimes internal energy and thermal energy are used interchangeable, but they really are not. Internal energy is the total kinetic energy of the object plus its potential energy. That kinetic energy is the thermal energy. And we kind of mentioned this before, but the potential energy has to deal with how far apart the the particles are, or molecules, within the, whatchamacallit, oh my goodness, object, right? So we talked about how liquids and gases are going to have more potential energy, specifically gases having the most potential energy, because in a gas, there's no specific volume, so the particles can spread out very far, having a lot of potential energy. Now, we can also, of course, calculate heat transfer, and this is where you're going to have maybe some flashbacks of chemistry, right? So if we want to calculate the heat transfer, right, or calculate how much energy it takes to change an object a certain temperature, we're going to use the well-loved Q equals mc delta T, right, where Q is the energy added or removed, because we certainly can have a negative Q. That means we've lost some of our thermal energy, right, through some sort of contact with a colder object. The M stands for the mass of the substance. The C stands for the specific heat, which is the amount of energy required to raise 1 gram, 1 degree Celsius, right? Pay attention to the units of specific heat. Sometimes you are given it in grams, which means your mass needs to be in grams. Sometimes you're given it in kilograms, which means your mass needs to be in kilograms. Okay. So conductors of heat, things that are good at moving heat, they're going to have a low specific heat, whereas insulators, things that are good at holding their heat, they're going to have a higher specific heat. And then delta T, of course, is the change in temperature. So T final minus T initial. Now, technically, this should be in Kelvin, but because Kelvin and Celsius scale linearly from another, and this is a change in temperature, not a temperature, it actually doesn't matter, right? The difference between 273 degrees Kelvin and 283 degrees Kelvin is 10. Right? 273 degrees Kelvin is going to correspond to 0 degrees Celsius, and 283 degrees Kelvin is going to correspond to 10 degrees Celsius, and that's also a change of 10 degrees. So it doesn't really matter which scale we're in because it's a delta T. Now, where that will matter, of course, is if you're trying to find a T final or a T initial. So just pay attention to what your scale is in. Now, normally this specific heat is in degrees Celsius, so you'll usually see temperatures in degrees Celsius. All right, that is it. You are now going to move on to the intro to heat and temperature packet. The answer key is, of course, on Canvas for you.